Okay, perfect. Grazie. So, good morning. The first topic of today is based on a very old class of antibacterial agents. This class represents the first family of compounds used to treat bacterial infections. Today, only one prototype of this class remains on the market, but it is still in use, and we'll see its potency, its pharmacological spectrum. This class really, at the beginning of the 19th century, represented a revolution in the therapy of infections, because in that time, nothing, perhaps some plant extracts, in that time were used to treat infections. But no other compounds, no other drugs. And the idea in that time was to use some dyes, some colorants, synthetic colorants, used, I think, just now, to treat the wool. In particular, in that time, they decided to explore the ability of some deep red dyes, deep red colorants, to treat infections in rats. But why two chemists and one pharmacologist, Mitch and Klarer, the two chemists, and the pharmacologist was Gerhard Domack, why they decided to explore, why they decided to try this compound directly on infected rats? Their hypothesis can seem very simple today, but in that time they had no any equipment, any apparatus, nothing. And so really it was a new concept of the drugs. In that time they thought that this compound, you see the chemical structure, these compounds are able to interact with the wool. As you know, wool is formed by fibers, natural proteins. And you know this, because when you want to wash a pullover, if you use the wrong program in wash machine, your pullover can be restricted, if you know, because we can lose the tertiary and quaternary form of the proteins of the wool. And so, really, their idea was new in that time, and they tried to inject directly in infected rat this compound. You see two aromatic rings at the azo group, in the middle with a double bond. So there is an extensive electronic cloud, and this effect can justify the property as colorant of this compound. These three scientists worked in that time in an important company called IG Farben Industry. Farben in German means colorants. And in that time, this company synthesized a lot, tons of different colorants. To see the first preparation of this compound, you can see the deep red color. The commercial name was Prontosil rubrum. Rubrum means red in Latin. And you see the color. But the problem in that time was to understand the mechanism of this compound, why this compound acts as an antibacterial compound, why this compound is endowed with this important activity. They didn't know anything. In that time, they knew only the chemical structure of the compounds. And so for several years, this compound was used for the treatment of infection, but the mechanism was unknown. Some years later, some scientists tried to identify the active compound, the active part of the molecule. And in that time, they analyzed the urine of the treated rats to identify what kind of compounds were present as metabolites in the urines of the rats. And in that time, they found two main components. This 3-amine benzene, you see, 3 amino group on a benzene ring, and another one, this 4-amino benzene sulfonamide. If you see these two structures, starting from the red colorant, you can see that our metabolism is able to reduce the diazo double bond and to split in two parts this molecule. So, in the blood, we have two molecules, a benzene derivative, 3-amino benzene derivatives, and a sulfonamide. So the scientists wanted in that time to know which of these two compounds were effective. And so they treated bacteria culture, bacterial mold, with these two compounds to verify which of them was active. And they found that the active compound was 4-amino-benzene sulfonamide and not the 3-amine derivative. So this discovery opened the way to the transformation, modification of this type of structure with the synthesis of a lot of derivatives of 4-amino-benzene sulfonamide. But the problem related to its mechanism still remain, because the scientists didn't know why this compound was so effective against the bacteria. Some years later, other scientists compared the chemical structure of this benzene sulfonamide with the chemical structure of a well-known natural compound called para-aminobenzoic acid. You see, para-aminobenzoic acid, PABA. Why this PABA is so important for the life of cells, of mammalian cells, but also for bacterial cells? Here, small picture here, you can see the chemical structure of tetrahydrofolic acid. Tetrahydrofolic acid is very important for the synthesis of DNA bases. In particular, this compound is a donor of methyl of carbon unit. You can see here FH4 tetrahydrofolic acid is able to donate 4 mil unit or methylene unit or methanol unit. You see a carbon unit with different oxidation state. And these carbon units are important for the synthesis of purines, so you know, or DNA bases. In the structure of tetrahydrofolic acid, you can see in the middle the residues of the para-aminobenzoic acid. So para-aminobenzoic acid is one of the components of the chemical structure of this important compound. We go back again, and here you can see the dimension of the 4-amino-benzene sulfonamide, which are very similar to the dimensions, the volume, the length of para-aminobenzoic acid. This means that when bacteria wants to synthesize tetrahydrofolic acid, it needs the presence of para-aminobenzoic acid, but due to the lack of control of this pathway, this bacteria can use this type of compounds, this para-aminobenzene sulfonamide, and in this case, this microorganism can incorporate this isoster instead of the para-aminobenzoic acid. The incorporation of this compound in this false.
The bacteria can use the aminobenzene.
Yes, normally they use this compound, but if there are.
No, I mean instead of the powder.
Yes, instead of PABA, yes. Because you see, they have the same dimensions and the same properties, same acidity. And so, from an external point of view, the two molecules seems very similar. Same electronic clouds, same electronic properties. But the incorporation of this false substrate blocks the pathway of the synthesis of tetrahydrofolic acid. But why this agent is so selective? Why this agent is active only against bacteria, not against mammalian cells? It is important to know that mammalian are able to absorb directly tetrahydrofolic acid from diet, from spinach, from vegetables. This is one reason because vegetables are so important. While bacteria are not able to absorb directly this compound, but they have to synthesize this compound, and so they need the presence of para-aminobenzoic acid. This is the reasons of the high selectivity of this sulfonamides, because only bacteria can incorporate sulfonamides in a false tetrahydrofolic acid. This means that the pathway of the biosynthesis of this compound, tetrahydrofolic acid, is blocked, is stopped. So first of all, we can see the dimension of these two compounds. You see the length is more quite the same. The acidity is quite the same. We'll see that these protons are acidic, like this carboxyl group. An amino group in para position, so we have the same effect. Here you can see how tetrahydrofolic acid is so important from the cell. Tetrahydrofolic acid is important, as I told you before, as donor of methyl unit. Here you can see the transformation of the oxyuridylate in the oxytimidylate. So we need the insertion of a methyl group on the backbone of uridine. tetrahydrofolic acid is able to introduce this type of group. You see here the pteridyllic group, here there is the chain para-aminobenzoic acid, and this is the carbon unit that can be donated to the uridine to form thymine. Here you see the mechanism, but I am not interested in the mechanism, just to show you how tetrahydrofolic works as methyl unit donor. In this picture, you can see the biosynthesis of tetrahydrofolic acid. Here you can see that this compound is formed by three main units. The pteridyllic group here, the para-aminobenzoic residues in the middle, and the last group is an amino acid, is a glutamic residue. These three units are important. They form the tetrahydrofolic acid. And so the biosynthesis is based on the formation of this final compound by forming the right bonds between the different units. So the starting point is represented by the pteridyl group, you see here. There is an alcoholic group that can be activated by ATP. And then there is the intervention, the para-aminobenzoic acid with the formation of this first bond between the nitrogen atom and the activated alcoholic group. And then the last step, you can see in the last step there is the formation of an additional bond between the glutamic acid and the carboxylic group. At the end, there is the reduction of the double bond from dihydrofolic acid to tetrahydrofolic acid. Here you can see a sulfonamide. This sulfonamide is able to compete with the para-aminobenzoic acids, and so you can see there is the formation of this false product. This false product can block the biosynthesis of the tetrahydrofolic acid, also by feedback, because you know that if we have a lot of the final compound, the synthesis is blocked at the beginning by a feedback process. So you can understand the mechanism of the sulfonamide. Sulfonamide is able to compete for the dihydropteroate synthetase, this enzyme, DHPS. There is a competitive inhibition of this enzyme, and the result is the block of this important pathway. But they stop in only one point of this important pathway sometimes is not enough. Because you know that the bacteria are able to bypass this step. And so some years later, other scientists discovered another compound called trimethoprim, able to inhibit the last step of this biosynthesis, able to inhibit this enzyme called the dihydrofolate reductase. And so the scientists decided to associate these two compounds, a sulfonamide with the trimethoprim, in order to have a synergistic effect in the blocking of this important pathway. So now on the market you find commercial product which contains these two compounds, a sulfonamide and an inhibitors of dihydrofolate reductase. It is really a synergistic effect, and this compound is still on the market, still used against intestinal infection, against as antimalarial, and so on. So this class is not so important, but it is an example of the discovery in the medicinal field, and how we can put together two drugs in order to have a synergistic effect. Synergistic effect means that if we put together these two compounds, we have a very high, a very potent effect, more than the simple effects of each compound. Once again, I remember you the selectivity of this class of compound, of benzene sulfonamide. Once again, I remember you that the mammalian are able to absorb directly tetrahydrofolic acid from diet, from vegetables, broadleaf vegetables, you see. While bacteria have to biosynthesize this compound, this tetrahydrofolic acid, by put together these three basic units: pterydyl alcohol, parabenzene, para-aminobenzoic acids, and glutamic acids, an amino acid. Chemistry and structural activity relationships. A brief description of this point, because as I told you before, only one prototype is still present on the market. Just to underline the difference of these two nitrogen groups. The para-amino group is an anilino group, is almost basic. It's a basic, but not a strong base, because you know the lone pairs is shared on the aromatic ring. The behavior of the other nitrogen atom is quite different. It has a proton with a substituent, you see R1. This proton is acidic. But why? Because you can see the minus charge can be delocalized on the two oxygen of the sulfonamide group. So we have a stabilization of the base. So we have a basic group here in paramino position, an acidic group in the other, in the sulfonamide group. Two different behaviors. Here on the table, you can see different sulfonamides, but only sulfamethoxazole. You see here the substituent here is an heterocycle, is still on the market. You see the pKa 6, acidic, liposolubility, MIC against the Escherichia coli, and the shelf life of this drug. The other drugs are no more present on the market because they are old. And so only this prototype remain on the market. Remain on the market for human infections. But in veterinary, this compound, the other compounds are still used. Why in the veterinary, yes, and not against human infection, and not in human infection? Because in veterinary, we have to use a big amount of compounds. You can imagine, you have to treat animals with a big weight. A cow, for example, it's a lot of kilograms, and so we need a big amount of compounds, and these compounds can be metabolized, in part metabolized, in part not, and these compounds go on the wastewater. So these drugs go in the river, and they can be responsible for the formation of the resistant strains. So in veterinary, normally only old antibiotics are used, antibiotics that are no more active in humans infections. This is the reason why veterinary, some sulfonamides are still in use. Sulfamethoxazole, it is used against intestinal infections as antiprotozoal, antimalarial, so it is effective against this type of infection. As I told you before, this compound exists, is present in combination with trimethoprim in a preparation called Bactrim in Italy. Trimethoprim is a dihydrofolate reductase inhibitor. So these are the chemical structure of the two compounds. Here you have the chemical structure of sulfamethoxazole. You can see the sulfonamides part with this heterocycle. And the other one, trimethoprim, is an inhibitor of dihydrofolate reductase, which is the next chapter of today. So we'll see this type of compounds in the next chapter. This association is active against the gram-positive and negative, very used, very common in veterinary. Now little in humans due to the presence of resistant strains. So normally cephalosporins, penicillins are preferred instead of this class. Nevertheless, this compound is very common in diarrhea, to treat diarrhea. It's my suggestion, when you go abroad, please take with you bactrim because it's useful. Sometimes if you can take an intestinal infection by diet and so on, and bactrim is very useful. The last slide of this chapter, you can see a summary about the structure-activity relationship of this class. Just in general, because you know only one prototype is present on the market. However, in the past, some substituents were present on the paramino group just to limit the absorption of this compound in the intestinal district and not to avoid the systemic absorption. These two groups, the paramino group and the sulfonamide, should be in para position. But if you remember the chemical structure of paraminobenzoic acids, you understand this chemical feature. It is important to have the same structure, so the two groups should be in the para position. You can find some heterocycle on the sulfonamide group, and this heterocycle can influence the acidity of this proton. And
sorry, Prof.
yes, please.
You are not sharing the screen.
Okay.
I can only see your face.
Yeah. Okay, just a moment.
Thank you.
Yeah. I try again. And now, can you see the slide?
Yes, perfectly.
Okay.
Thank you.
Okay, thank you. And the sulfur group can be replaced by other function. The important is to maintain the right acidity of this proton, because the acidity of this group should be comparable with the acidity of the paraminobenzoic acid. So we have to maintain the same acidity of the two groups. Okay. Have you any questions about this topic, about this group? Anything is not clear? No questions? At home, have you any questions? No?
No, so far.
Okay. So. Allora, adesso andiamo su un altro capitolo. Just a moment. The next chapter, you see, is related to dihydrofolate reductase inhibitors. Just a moment, where the biosynthesis is not here. Just a moment. Okay. I want to show you again the biosynthesis. Just a moment. Oh, yeah. Here. Impossibile condividere l'audio. Can you hear me at home? No?
Yes.
Ah, okay. Okay. I don't know why. Yeah, this. Okay. So, once again, I want to show you how these inhibitors work. As I told you before, they are active, they are able to inhibit the last enzyme involved in this important biosynthesis, in this important pathway. Here you can see the chemical structure of trimethoprim, and this compound is one of the most potent inhibitor of this enzyme. This means that these compounds are able to block the formation of the tetrahydrofolic acid, which is the active form of the folic acid.
They inhibit the formation of dihydrofolic acid.
Tetrahydrofolic, the last one. The last one is the active form of the folic acid. It is necessary the reduction of the double bond of dihydrofolic acid in order to have the active form. If we have not the reduction of the double bond, the folic acid is not active. And so in this way we block the formation of important DNA bases. Okay, just a moment. I open again the other chapter. Okay. Don't see the slide. Why? I share again. Just a moment. Okay. Dihydrofolate reductase is the enzymes responsible for the reduction of the hydrofolic acid to tetrahydrofolic acid. We have already seen this step. This acid is important for the vital processes of the life. You see here where tetrahydrofolic acid where it's important, this compound is a donor of a carbon unit, and so it is able to take from the sources, serine, glycine, histidine, and other compounds. It's able to take the carbon unit and to transport this carbon unit to the products. Purines, you see, DNA bases, vitamins, serine, and thymine, and so on. How this compound works? As I showed you before, tetrahydrofolic acid is able to take a carbon unit This carbon unit form a bridge between these two nitrogen atoms. One is present on the pteridylic group, the other one is of the para-aminobenzoic acid. And this carbon unit can be donated to, for example, to uracil to form a thymine. You see a carbon unit that can be incorporated in this DNA base. We know exactly the structure of this enzyme. It was possible in the past to crystallize the crystallization of this enzyme. And so, if you go on the PDB website, where you can find a lot of crystallized enzyme, it's possible to know the chemical structure of the active site, of the binding site of the enzyme. Here you can see inside the binding site the presence of the product, tetrahydrofolic acid. You see here the chemical structure. And in this way, it was possible to design specific inhibitors of this enzyme. This enzyme has been isolated from several sources, mammals, bacteria, and so on. The problem is that the binding site of bacteria is very similar to the binding site of mammalian cells. And so it is not so easy to have selective compounds able to inhibit a specific enzyme, bacterial enzyme, instead of a mammalian enzyme. Yes?
I didn't understand. You said that.
Okay, the structure of the two bacterial and mammalians, the structure of this enzyme is quite different, but the active site, the binding site is very similar.
Yes, but I don't understand, because if you want to take tetrahydrofolic acid from the diet, why do you have to do that?
Okay, yes, but this is the case of sulfonamide. But if you want to design other inhibitors, the sulfonamide inhibit another enzyme, if you remember, the dihydropteroate synthetase. Now we are talking about inhibitors of the last step, of the dihydrofolic reductases. Tetrahydrofolic reductase, you see? I show once again. Just a moment. Oh, okay. Just a moment. Sulfonamides are able to inhibit the DHPS, dihydropteroate synthetase. Okay? But now we are talking on another enzyme called dihydrofolate reductase. This one. If you want to design specific inhibitor of these enzymes, we have to know the binding site of the bacterial enzyme and the binding site of mammalian enzymes if we want to have a selective inhibition. Is it clear? Yes? And the problem is related to the selectivity of these inhibitors. Because we can have potent inhibitors of this enzyme, but not selective. Or we can have less potent inhibitors, but selective. We'll see now this problem. Just a moment here. Okay. Yes. We know the chemical structure, we know the we have the crystallographic picture, structure of bacterial enzyme, but also we have the chemical structure of mammalian enzyme. So we know the differences between these two enzymes, but the binding site is very similar. The two binding sites are very similar. And so it is not easy to design selective inhibitors of these enzymes in bacteria and of these enzymes in mammalian. In particular, you can read here, it has been seen that the amino acids associated to the binding area of the substrate are very similar, indicating the high degree of structural homology. This is the problem. We can have potent inhibitors but not selective. This means that we can use these potent inhibitors to kill bacteria, but also they are able to kill our cells. And so we have, in this case, severe side effects. Is it more clear now or not? Yeah. We have two different classes of DHFR inhibitors. Classical and non-classical. The difference between these two classes is due by the presence of the glutamic acid residue. If you remember, tetrahydrofolic acid is formed by three basic units: pteridyllic group, para-aminobenzoic group, and glutamic acid residue. These three units form the tetrahydrofolic acid. The presence or the absence of glutamic residue is responsible of these two different classes. Classical inhibitors. You see here the chemical structure of folic acid. Once again, you see the two double bonds. So if you want to activate folic acid, these two bonds should be reduced to tetrahydrofolic acid. Okay. Some years ago, when the scientists didn't know the active site of this enzyme, they wanted to design new inhibitors starting from the chemical structure of folic acid. So in that time, they tried to modify the chemical structure of folic acid in order to find new, more potent inhibitors of this enzyme. So Folic acid represents the lead compound, the starting point. And they wanted to modify, but the problem was how we can modify the chemical structure of folic acid. What kind of approach we can apply on this molecule. If you remember at the beginning of the course in the introduction part, I described you what is an isoster. Isoster is an atom with the same electronic cloud, with the same number of external electrons. This means that it's possible to replace an oxygen atom with an amino group with two hydrogen, because they have the same number of electrons. And in that time, the scientists replaced the oxygen group with an amino group, just to follow the rules of the isostery. But you know the electronic properties of an amino group, and the electronic properties of an amino group are very different from those of an oxygen, because you know that an amino group has a lone pair that can be shared, can be delocalized on this aromatic ring. This means that we have an increased basicity of this nitrogen atom, because there are more electrons inside the aromatic cloud. This means that this nitrogen atom can be protonated at physiological pH. You see here the chemical form of the protonated methotrexate. The name of this compound is methotrexate, you see. You see the protonation of this nitrogen atom in this heterocycle. This protonation is not possible in the folic acid. And this protonation is possible in the methotrexate because there is an increased density, electronic density, on this aromatic ring. But why this protonation is so important for methotrexate? This protonation is important because in the binding site, just very close to the region where is allocated this nitrogen atom, there is a residue of an aspartic acid, CO minus. Remember you, aspartic acid is an acidic amino acid with an acidic residue. This means that it's possible the formation of an additional ionic bond between methotrexate and the binding site. This means that methotrexate is able to bind in a very potent fashion, is able to interact with the active site by blocking the binding site, and the presence of methotrexate in the binding site does not allow the allocation of the natural substrate, which is the folic acid. So the binding site is already occupied by the methotrexate, because methotrexate has a very high inhibition constant, 10 to 10 molar. You see here, 10 to 10 is like a toxin. This high inhibition constant is due by the ability of methotrexate to give an additional hydrogen bond with a aspartic residue present in the binding site. So you can understand the surprise of the scientists in that time when they saw that a little difference, an oxygen instead an amino group, was able to increase in this fashion, this manner, this way, the inhibition constant of methotrexate. In that time, they didn't know the reason, but they found this result. And so some years ago, they discovered this potent inhibitor of the dihydrofolate reductase. But this compound is very potent, but not selective. This means that if you use methotrexate against a bacterial infection, you can also kill our healthy cells. This means that methotrexate is not an antibacterial compound, but it's used against to treat cancer. So sometimes the discovery of antibacterial agents is very close to the discovery of anti-cancer compounds. This is the case. The same case is for quinolones. Some quinolones are now used as anti-cancer compounds because, you know, the machinery of the cells are very similar. Yeah.
In case of anti-cancer drugs, there is also the problem of cancer cells and normal cells.
Yeah.
So,
in fact, methotrexate has a very severe side effects. But we are lucky because you know that cancer cells, they have a faster cell cycle. And so we can kill only the cells with a faster cell cycle and not the normal cell. But there are several cells with this faster cell cycle, for example, cells in the intestine, cells of the hair. So the side effects are due by the interaction of these compounds with the healthy cells with a faster cell cycle. Yeah.
I just missed a point about methotrexate. You just said that it gives an additional hydrogen to what?
Yeah, to a residue of an aspartate. You see here,
Okay.
aspartate 27, which is present here in the binding site.
So that's why it blocks the binding site.
to the,
That's why it's blocked the binding site.
yes, it's in, yes. Because folic acid is not protonated. This nitrogen atom of folic acid is not protonated because it is not so basic. While the substitution of the oxygen atom with an amino group increase the basicity of this nitrogen atom, and this nitrogen atom is protonated, so it has a positive charge and can interact with an aspartic residue with a minus charge. You have an additional ionic bond. It's clear? Yeah? Okay. Other questions? No other questions? Okay, so we can stop now for 20 minutes. We start again at 11:30. So we drink a coffee. Okay. Okay. Okay, dear students. So we have already described why methotrexate is so potent, because it is able to form an additional ionic bond. Here you can see the other structure activity relationships of this compound. You see it is important, the pteridinic group. If we replace the amino group with a sulfur, we have a decrease in activity, because sulfur is not so basic as the amino group. Hydrophobic bonds due to the pi-pi interaction with the binding site. Hydrophobic bonds again with the second aromatic ring. Hydrogen bond with this acidic function. Okay. As you can see here in blue, there is the residue of the glutamic acid. The presence of glutamic acid is important to classify this compound as compound of the first class, the classical compound. Here you can see the importance of the three building blocks, of the three units of methotrexate. You can see the first part, the pteridinic group. In this case, the IC50 is very high, 21,000 nanomolar. If we add the residue of methylaminobenzoic acid here, so we have the two building blocks, the IC50 is 88 nanomolar. If we add the last part, the residue of the glutamic acid, we have the IC50 1.3 nanomolar. So it is very, very potent. So you can understand the importance of the three units, of the three building blocks that form methotrexate. Non-classical inhibitors. Non-classical means that there is no the residues of glutamic acid. The most important compound of this class is trimethoprim. We can analyze very carefully the chemical structure of this compound. You can see there is a pyrimidine ring with two amino groups. This ring is also present in the first generation, in the classical, in DHFR inhibitor. So also in this class we can find this ring important for the interaction with the binding site. But the structure is more simple. There is only another aromatic ring with three trimethoxy groups. So this second ring, also this second ring has an high electronic density, because you know the chemical properties of the methoxy group on an aromatic group. They can increase the electron density of this aromatic ring. Trimethoprim represents the first and the most important compound of this class. Trimethoprim is used against intestinal infection, as antimalarial, as antiparasites. Yes. The second example is pyrimethamine. Pyrimethamine has the same aromatic ring, pyrimidino, you see, the two nitrogen atom and the two basic group on the ring, with another aromatic ring directly connected with the pyrimidino ring. Also, pyrimethamine is used mainly as antimalarial drug. We'll see in the next chapter the drug used against the Plasmodium malaria, you know. And then the last two compounds of this class are proguanil and cycloguanil. Proguanil is the open form of cycloguanil. Cycloguanil is formed by our metabolization. So it was observed that the administration of proguanil, the open chain analog, the proguanil is transformed by our metabolism in cycloguanil. So the scientists thought to administrate directly cycloguanil instead of proguanil. This compound is mainly used as anti-malaria drugs. All these compounds are less toxic against mammalian cells in comparison with the methotrexate. But also they are less potent against bacteria and against Plasmodium and other microorganisms. Okay, here the description of the four compounds. This table is very interesting. It is in Italian, but it is easy to understand. We have four different microorganisms: Plasmodium berghei, you know, malaria; Escherichia coli, the bacteria; Staphylococcus aureus is another bacteria. And then we have cell of rat liver. Rat liver, you know, is a mammalian cells. This table, it's useful to understand the selectivity and the potency of this class of compound, this class of inhibitors. You see the IC50 value 10 to -8 molar. We can see the first example, methotrexate. We have already described the high potency of this compound. But, for example, methotrexate is not active against the Plasmodium. So we can not use this compound as antimalarial. No activity. But please see the high activity against Escherichia coli and against Staphylococcus aureus, 0.01 for 10 to -8. So we are in the range of 10 to -10 molar. Very, very potent. The same potency against Staphylococcus aureus. But the problem, if you see, is the same toxicity against rat liver cells. This means that methotrexate is very potent, but it is not selective. High toxicity against the mammalian cells. If we see the profile of trimethoprim, you can see that trimethoprim is active against Plasmodium, so we can use trimethoprim as an anti-malarial drug. Is also active against Escherichia coli, 0.7 for 10 to -8, so 10 to -9 molar. The same activity against Staphylococcus aureus, but if you see 35,000 against rat liver cells. So trimethoprim is not toxic. We can use this compound against Plasmodium, against different strains of bacteria, without any toxicity for mammalian cells. This is very important. So trimethoprim is really an effective antibacterial drug with very few side effects. More recently, the scientists try to modify the backbone, the chemical structure of trimethoprim in order to increase its activity as an antibacterial drug and to kill resistant strains. Here you can see some modification performed on the chemical structure of trimethoprim, in particular trimethoxate. You see there is once again the pyrimidine ring with another aromatic ring, and then you see the residue of the trimethoprim, the trimethoxybenzene ring. The same manner you see the modification performed to give pyritrexine, another pyridine ring with the same dimethoxybenzene ring. These two compounds are more recent than trimethoprim, and they approved by FDA, Food and Drug Administration is the American Health Agency. And this compound were introduced in Italy, trimethoxate as antiprotozoal, pyritrexine as anti-cancer. Probably pyritrexine is very active against mammalian cells. It's more potent against mammalian cells. Why malaria parasites are resistant to this type of inhibitors? This point is important to understand the resistance, the basis of the resistance of bacteria, parasites, and other microorganisms. Here you can see the chemical structure of pyrimethamine. Pyrimethamine is one of this type of inhibitors. And here you can see the interaction of pyrimethamine inside the active site of the enzyme. In particular, you see the interaction of these two nitrogen atoms with an acidic residue, of D54, I think it's an aspartate residue. Also, you can see this NH2 able to give hydrogen bonds with the two carbonylic residues. And also you can see the accommodation of the parachlorobenzene ring in this position. Very close to this serine 108. In the resistance strain of plasmids, it was observed a substitution of this serine 108. You see, you remember perhaps the peculiar group of serine is the alcoholic OH, you see here. In the resistance strains, it was observed the substitution of this amino acid, this S1, this serine, with an asparagine. Asparagine is bigger than serine. Asparagine has this final amido group, amido group, is an amide. This means that in the active site, the space is more restricted. And in particular, it is difficult to accommodate this parachlorobenzene ring because there is a steric clash between the two electronic clouds. You see here the chlorine atom is very close with the amido group of the asparagine 108N. And so you can understand how a light modification, only one amino acid in the binding site, can influence, can prevent the right accommodation of an inhibitors, as in this case. We'll see other example of resistance due by a mutation of only one amino acid. So it is very important to understand why some strains are resistant, because it is possible to modify the chemical structure of the inhibitors in order to overcome this type of resistance. Is it clear? Yeah. Is it clear at home?
Yes.
Yes. Okay. Okay, dear students. The last point of today is the synthesis of trimethoprim. It is a very easy synthesis. You see only 2 steps. It's not so difficult. As I told you before, it is important to understand how we can simplify, just a moment, the chemical structure of the final compound. So First of all, you can draw the chemical structure of trimethoprim. It's not so difficult. We have now this one. Okay. 1, 2, 3, 1 here, 4, 3 here, 2, the other one is here. Okay. So, if you see the chemical structure of trimethoprim, you can see that there is this part of the molecule.
Raf, you are not sharing.
Ah, okay, yeah, okay, sorry. Just a moment. Here, okay. I think now it's
Just now it's fine.
oh no. Just a moment, so I check. Okay. So perfect. Okay. So we can cut okay, this one. The molecule in these two positions. And if you see, by apply retrosynthesis, okay. Just a moment. Use this one. It remains. Just a moment. This residue called guanidine. So guanidine is the one of the starting reagent important to design the trimethoprim. Guanidine is a very basic compound. You see 3 nitrogen atoms, basic nitrogen amino functions, and so it's very, very basic. It's able to give nucleophilic substitutions. The problem is to form this bridge, this methylene bridge. So we can cut again. Just a moment. Cancel this compound. And we have, it remains a very strange residue. In particular, we need a reagent with the 2 good leaving groups. because we have a guanidine with the two basic nitrogen atoms. These two basic nitrogen atoms are able to give nucleophilic substitution. So we need a reagent with the two optimal leaving groups.
Now we're doing electrosynthesis. So from the end.
Yes. Okay, this is a retrosynthesis. But now we see now the real synthesis. It's just a comment. So we need the guanidine as a starting reagent, but also we need another reagent with the two optimal leaving groups. This is the problem. So now we can see again the synthesis on the slides. Yeah. Which are the two groups? You see here, we have this part of the molecule of this intermediate. We have an ethoxy group, OC2H5, you see, which is a good leaving group. And we have also an nitrile. In particular, we have two carbon atoms which have a partial positive charge. Why? The carbon very close to the nitrogen in a nitrile group, you know, the amino group, the nitrogen group is more electronegative than a carbon, so we have a partial positive charge on this carbon. And the other carbon is very close to the oxygen of the toxide group, toxic group. Also in this case, we have a partial positive charge. So these two carbons can be attacked by guanidine to give trimethoprim. Now the problem is to synthesize this intermediate. We can start from a simple aldehyde, benzoaldehyde, trimethoxy, benzaldehyde. And we can put in the mixture these 3-ethoxy propionitrile. Is a derivative of the propionic acid. Perhaps you remember the name of the nitrile is related to the name of the organic acid. So we have from acetic acid, we have acetic nitrile, propionitrile from propionic acid, and so on. We have an aldehyde, and we have this carbon with the two hydrogen, acidic hydrogen atom. If you see the first step, in the first step, it is necessary the presence of a strong base. What means a strong base? Here. So, just a moment. Just a moment. We have an aldehyde here. H plus triple bond this one, okay, N, e quindi C2H. We have these two protons very close to the nitrile group. Nitrile group is more electronegative, so we have these two protons are acidic. This means that it's possible with a strong base to take away one of these protons and to have a negative charge in this position. This negative charge is unable to attack the carbonyl group of the aldehyde. But it is important at this point to understand what means a strong base. Normally, you know sodium hydroxide. Perhaps you know sodium hydroxide is a strong base for you. You know ammonia, another base, not too, perhaps less stronger than sodium hydroxide. But in this case, these two bases are not able to take away this proton. We need a stronger base. How it is possible to have a stronger base? Here you can see sodium methoxide. This means that we can take methanol and in some way we have to take away a proton from a methanol to have methoxide. Perhaps plus a proton. If we write this reaction during an exam of organic chemistry, you go at home, because an alcohol is not an acid. It's not possible, this type of reaction. On the other side, you can understand that if some way we have this type of anion is a very, very strong base because it derives from a very weak acid. The conjugate base is very strong and the starting acid is very weak. How we can form sodium methoxide? It's a very simple reaction. We can put together methanol plus metallic sodium. If we put together these two compounds, it is an exothermic reaction. We have the formation of hydrogen, half molecule of hydrogen, plus sodium methoxide. This is a redox reaction. In this way, we can have a very, very strong base because we have a salt of an alcohol, anion. There is another example of a very strong base. Sodium amide, NaNH2. Normally, you know ammonia, NH3. NH3 is a base. It is not an acid. How we can transform this base in an acid? We can make a reaction of liquid ammonia. Liquid ammonia, we have liquid ammonia at minus 80 degrees. Minus 80 degrees, we have liquid ammonia. You know ammonia is a gas, a normal condition at room temperature. But if we work at minus 80 degrees, we have liquid ammonia. It's possible to condense liquid ammonia. In the liquid ammonia, we can put inside some small pieces of metallic sodium. So ammonia plus sodium, we have once again an half molecule of hydrogen plus sodium amide, Na. So we have take away a proton from ammonia. Ammonia is not an acid. Ammonia normally cannot lose a proton because it is not an acid. But in this case, if we apply a redox reaction, it's possible to have sodium ammonia. Sodium ammonia is the conjugate base of a very weak acid. And so sodium amide is a very strong base because it's the conjugate base of a weak acid. Is it clear? Atom, is it clear? Have you any question, Atom?
No, it's clear. Thank you.
Okay. So we have now the most strongest bases, sodium amide or sodium methoxide. These two bases are able to take away this one proton present in alpha position to the nitrile group. So it is possible to have the formation of a partial negative charge or a negative charge, a full negative charge. This negative charge is able to attack the partial positive carbon atom of the aldehyde function. In this way, it's possible to form a carbon-carbon atom, bond, sorry. It's not so easy in organic chemistry to form a carbon-carbon bond. Why? Because if we want to form a carbon-carbon bond, we need a negative carbon atom able to attack a positive carbon atom. So we have to generate these two species, but in particular, the negative carbon atom. If you put together these two charged species, we have the formation of a double bond between the two reagents. Just a moment. Here. Okay. Okay, at the beginning we have the formation of the OH group on the carbonyl atom, okay. And then we can lose a molecule of water, and then we have the formation of a double bond. So you see dehydration. So we have the formation of a double bond. Here perhaps we can do better, just a moment. So you see. So for this step, we need a strong base able to take away a proton in alpha position to the nitrile group to form an anion which is able to attack the positive charge, the partial positive carbon atom of the aldehyde function. We have lost a water molecule, and so you can see the formation of a double bond. Which is now the situation? We have two positive carbon atoms. The first one is in the nitrile function. And the second one is very close to the toxic group. If we react this compound with the guanidine. We can draw again, just a moment. These two amino groups have their lone pairs. These two lone pairs are able to attack directly the first one, the carbon atom, the nitrile group. The second one, the carbon close to the oxygen. So we have another hydrogen here. Without, okay, partial positive charge. In particular, you can see one leaving group. A leaving group is this, a toxic group, while in the other group there is a nitrogen, which can be protonated to give an amino group. So the last step is this one. We have the formation of the trimethoprim, thanks to the aromatization of the system. So the attack of the guanidine, the first amino group on the nitrile and the second amino group on the carbon close to the toxic group, it's able to form this pyrimidine system. Okay. Just a moment. Is a mistake. The nitrogen is this position. Okay, because you remember this is the residues of guanidine. Okay. So in this synthesis we have seen the use of strong bases necessary to take away these acidic protons, a condensation between a guanidine and two positive carbon atoms, and the formation of a pyrimidine ring. The synthesis of trimethoprim is quite simple, only 2 steps, and it needs the use of a strong basis, sodium methoxide, which is able to take away these acidic protons. Have you any questions at home? Classroom? We can see the slides. Just a moment. Here, just to finish for today. Okay. So you see the starting benzaldehyde. We can generate an anion in this position by using a strong base. The minus charge is able to attack the carbonyl of the aldehyde. We have lost a water molecule for when we have the formation of the double bond, and then condensation with the guanidine. So this is the synthesis of trimethoprim. Have you any questions? Okay, so we have finished this part of the program, and then next time we start with the anti-malarial drugs. Perhaps you already know the cycle of Plasmodium, but we can refresh the cycle, and I will show you the drugs against this disease. Okay, thanks a lot for your attention, and see you next time, 10 o'clock. Okay, next Thursday. Bye-bye.